One more lesson of building up the tools and infrastructure we need before actually getting into the real machine learning. In this lesson, we're going to cover some of the tools to evaluate our models. There are a lot of different methods and metrics that you can use, but I'm going to stick to covering the ones that we'll be using just in this chapter. So the first thing that we need to define is a holdout test set. This is a sample of data that's set aside and not used in any of the fitting of the model for the purpose of evaluating the model's ability to generalize to unseen data. So this is meant to simulate how the model will perform in real-world scenarios. So this is the entire point of building these models, to generalize and say something about the world. Now, given that concept of a holdout test set, hold that in the back of your mind for just a minute. We'll be primarily using k-fold cross-validation to evaluate our models. In this process, the full data set is divided into k subsets, and the holdout method is repeated k times. That is, in each iteration, one of the k subsets is treated as the holdout test set, and the other k-1 subsets are put together to train the model. The purpose is that this gives you a little bit more robust read on the performance of the model rather than just having one single holdout test set for the model to be evaluated on. Now you have k test sets and k evaluation metrics to understand the potential performance outcomes. Let's walk through an example of what cross-validation actually looks like to make sure we're all on the same page. In this example, we'll start with a full data set of 10,000 examples, and we want to run 5-fold cross-validation. So again, that means k equals 5. So the first step is to split that 10,000 example data set into k, or 5, subsets. So you'll see that we now have 5 subsets of data, and each has 2,000 examples. So this is sampling without replacement. So all 10,000 examples are still accounted for. And it's worth noting that these subsets will remain the same throughout this entire process. So an example in subset 1 will remain in subset 1 all the way through the end of this cross-validation. We assign one of these subsets as the test set, which is subset 5 in red here, and then we assign the other 4 that are in blue to the training set. Now we'll fit a model on the 8,000 examples in blue, and then we'll evaluate the model on the 2,000 example test set in red, and then we'll record the performance metric and store that away in an array. To be clear, this is all handled under the hood in scikit-learn. You don't have to manually implement these steps. You'll see when we actually write this with code that scikit-learn handles all this, but it's important for you to understand what it's doing when it carries out this process. Again, you'll pick an evaluation metric, and after the first iteration, it'll store the performance of the model on the holdout test set. So here we're saying that's 0.867. Next, we'll move on to the second iteration, where now the fourth subset is the test set, and subsets 1 through 3, along with the fifth one, are now the training set. So again, we'll refit a brand new model on these 8,000 training examples and evaluate on the 2,000 test examples in that fourth subset. And then we'll store the performance metric. Here, we're just saying that's 0.884. Then again, for the third iteration, the third subset will be our test set, and then the model will be trained on the 8,000 examples in the first, second, fourth, and fifth. So you train a brand new model, evaluate it on the third subset, store the performance metric. Here we'll say it's 0.901. Again, for the fourth iteration, same process as before, but now the second subset is our holdout test set. Last but not least, the first subset is the test set, and 2 through 5 are the training data. Fit a model, evaluate it on the first subset, and store the evaluation metric. Now, it's worth noting that at this point, every subset and thus every example has been used in a training set 4 times and in an evaluation set once. So we have now used this model configuration to fit a model on all different combinations of these examples and evaluated it on every single point in this dataset. So you can see why this can be a really powerful tool to gauge a model's ability to generalize. And then lastly, you would normally output maybe the full array of scores, so all 5 scores, or you might just output the simple average. So the average is 0.885. But now we see a more robust gauge of what the potential outcome of this model would be. So let's just say we're using a single holdout test set and using that to gauge the performance of the model for our business. Now the first iteration yielded a score of 0.867, but an average over all 5 is 0.885, and the highest is 0.901. So that's a difference of 0.018 from the lowest score to the average and 0.34 from the lowest score to the highest score. That may not seem like a big difference, but in a business setting where this could impact millions of dollars, that's a huge difference. So having a read on how this model performs over 5 different test sets is a huge advantage to truly understanding how your model might perform in the real world. Now, this gives us more confidence that the model will perform around 0.885 and gives us a range of plausible outcomes or some error bars on the projection. So let's talk about actual evaluation metrics now. So for a classification problem like the SPAM ham dataset that we're working with, we'll generally use 3 main performance metrics. The first is accuracy. So that's just the number that you've predicted correctly over the total number of observations. So if you have 10,000 observations and you got 800 of them labeled correctly, then your accuracy is 80%. The second metric is precision. Within the context of the problem that we're working with, that would be represented by the number that the model predicted as spam that are actually spam, divided by the total number that the model predicted as spam. And the last evaluation metric is called recall. So that would be the number predicted by the model to be spam that are actually spam. So again, that's the same numerator as precision, but now it's just divided by the total number that are actually spam instead of the total number that are predicted as spam. So that's accuracy, precision, and recall. So I like this visual representation of precision and recall. You can see that the numerator in both is the same, the amount that you correctly identified, but the denominator is different. Precision is all things that you said were relevant, while recall is all the things that are actually relevant. So in our example, relevant means it's spam. So now, precision and recall give you the ability to kind of tailor the aggressiveness of your algorithm based on your business problem. For instance, if false positives are really, really costly, then you'll want to optimize your model for precision. But if false negatives are really, really costly, then you'll want to optimize the model for recall. Only knowing accuracy may not really give you insight into this kind of trade-off, and we'll dive deeper into those specifics as we start to build our own models. So now that we understand some evaluation metrics that we'll be using, and we understand how to actually use those to evaluate the model, I think we're set to actually build some models.